So lecture 9, matrices as functions, looking at the 3x3 case. So we'll summarize what we did last time. We'll look at 3x3 matrices of function, an example with 3 leading ones, an example with 2 leading ones, and then talk about determinants for square matrices. So a little summary from last time. We looked at functions defined like this, where M is a 2x2 matrix and V and W are 2-dimensional vectors. And we found the following. The image is the span of the columns of M and is a subspace because it's a span. The null space is all solutions to MV equals 0. It's the solutions to the homogeneous equation, and that's also a subspace, but of the domain. The columns of M that correspond to the leading ones are linearly independent and span the image, so that's a basis for the image. The columns of M that correspond to free variables correspond to the null space, but you actually have to solve the equations to find the null space. And then finally, the dimension of the domain is the number of columns. And we see that every column is either a leading one or a free variable. So the dimension of the image is the number of leading ones. The dimension of the null space is the number of free variables. And that adds up to the dimension of the domain. So we want to look at how that works out for 3x3 cases. So suppose we have 3 leading ones. So here's a matrix M, and here's this reducible echelon form. We're not actually going to calculate that. We'll just say what it is. So define the domain, the codomain, and the image. What's the basis for the image? Why is the null space 0-dimensional? So the function is W equals M times V. Right? Our output is a 3x1 vector, and our input is a 3x3 matrix times a 3x1 vector. So our domain is 3-dimensional vectors. And our codomain is also 3-dimensional vectors. So we have a function from the set of 3-dimensional vectors to the set of 3-dimensional vectors. What's the image? So the image is the span of so that's the set of all vectors of the form K1 times 105 plus K2 times 216 plus K3 times 340, because those are the columns. We see here the columns are linearly independent because we have 3 leading ones and no parameters. And so the span, the dimension of the image is actually 3-dimensional because these are linearly independent vectors. So dimension of image equals 3. Dimension of null space equals 0 because there's no parameters. So there's nothing in the null space except for the 0 vector. Right? Because the 0 vector is always gets mapped to the 0 vector. So the null space is 0-dimensional. The image has dimension of 3. The domain has dimension of 3. So what do we find? 3 plus 0 equals 3. So good enough. So we can look at this picture sort of like this. I got these from GeoGebra. GeoGebra is a little flaky if you look at it in 3 dimensions. So that's why I don't want to actually try and the 3-dimensional version of GeoGebra tends to be a little flaky and sometimes it locks up. So I don't like to do that while I'm doing these things live. So in 3 dimensions, we have, let's see, which one is which? This red vector here is I hat. It's 1 unit in the x direction. So the red line is the x vector. J hat is the green vector. And then the blue vector is k hat, which is the unit vector in the z direction. So this is a basis for all of 3 space. And what we've seen is that any vector in the plane, once we know where these 3 things go, then we know where everything goes. So m times I hat is the red vector over here. We'll do this over actually down here. M times j hat is green, and m times z hat is red. And they're linearly independent. They're not all in the same plane. So how does this go? If I have some vector that is, some multiple of I hat plus some multiple of j hat plus some multiple of k hat. So we're talking about this vector. So if we call that vector that I just drew in there v, we call that, say, a times I hat times b times j hat plus c times k hat. Where does it go on the right? Well, a times m I hat plus b times m j hat plus c times m k hat. So if it's a times red plus b times green plus c times red there, it's going to be a times red plus b times green plus c times blue over here. And then we can add those 2 by 2. So we start by taking these 2 vectors. We form a little parallelogram in 3 space. We get that vector. That's the sum of this one and this one. Then I take this sum, and we draw the parallelogram. And so this vector here, which is my vector v, gets mapped to this vector. And the relationship of the vector v in the domain to the 3 vectors red, green, and blue is the same as the relationship of the vector in the image to the vectors red, green, and blue. So the structure is just transfer over pretty much. So that's not too bad. So what about, we have 2 leading ones and 1 free variable. Maybe I'll give myself a little space by pushing this up a tad. And then I need to push that back down. So here's the reduced row echelon form. So dimension of domain, it's a 3 by 3 matrix. Dimension of domain equals number of columns equals dimension of image plus dimension of null space. So that's 3. Dimension of the image is 2 because there's 2 leading ones, and the parameter corresponds to the null space. So we've got 1 thing in the null space and 1 dimension in the null space and 2 dimensions in the image. So basis for the image is these 2 columns, right? Because those correspond to the leading ones. So that's a basis. So our image is actually 2-dimensional because I've got 2 linearly independent vectors. The third one, this one, is actually a linear combination of these 2. So 2-dimensional. Null space, what's the null space equal to? Well, we just set up our parameterization. So we have x1 equals, x1 plus 2, x3 equals 0, x2 plus x3 equals 0, and we don't have an equation for x3. So that's taking this reduced row echelon form and turning it into a pair of equations. As to find the null space, the right hand side is 0. So there should, we could write this as 1, 0, 2, 0, 1, 1, 0, 0, 0, 0, 0, 0, like that. And then we convert this into these equations. So we'll set x3 to be equal to our parameter t. x2 then becomes minus t, and x1 is minus 2t. So our null space is that. So one-dimensional because it's the span of one vector. And the span of one vector is just a line. So two-dimensional image, one-dimensional null space, the image, find the leading ones, the columns that correspond to the leading ones is the basis, and then solve these equations to get the null space. Okay, so how do we think about this? So here's the function, red, green, and blue. These are our basis vectors in 3 dimensions. These are the images of the 3 of them over there. So red is I hat, green is J hat, and K hat is blue. So I hat goes to the red vector, J hat goes to the green vector, and K hat goes to this blue vector over here. So these are all in the same plane, right? That's this blue plane. So all 3 of these vectors lie in this blue plane. So again, a little bit tricky visualization, but sort of the best I could do with GeoGebra. So if I take a vector in 3-dimensional space over here, again, any vector in 3-dimensional space can be thought of as some multiple of I, right? Go in the red direction a little bit, go in the green direction a little bit, and then go in the blue direction a little bit. Here, if we do the same thing, since all 3 vectors in the plane, you're going to end up in the plane itself. So you go in the red direction a little bit, go down in the green direction a little bit, and then down in the blue direction a little bit. And you'll end up in the plane with a vector that's in this blue plane because all 3 of the vectors are in that plane. So the image is not equal to the codomain because the codomain is the entire 3-dimensional space, but we don't get all of the 3-dimensional space, we just get this one plane. So we lost a dimension along the way somewhere, and that's the null space, because we took a 3-dimensional thing and we squished it down onto a plane, which is a 2-dimensional thing. So what's another way to visualize this aside from using IJK? Well, here's 2 pictures. They're a little bit complicated. So let's explain these a little bit. Red, in this picture on the left, which is the domain, is I hat. So that's this vector here. It's a little bit hard to see, but it points along the red line. That's the x-axis. Green is J hat. That's that vector. And we know over here, red equals M I hat, green equals M J hat. And those 2 things are the first 2 columns that correspond to these 2, first 2 columns of the matrix. So red is the vector. I need to write these things down more. Red is the vector, what was that, -1, 1, 3, is 1, 1, -3. And green is the vector, the second column of that matrix, which is -1, 1, 2. We don't need the third vector because these two vectors actually span. They're linearly independent and they span this. So this green vector and this red vector, those are the only vectors you need. Okay, so what's going on here back in the domain? This is my codomain. This plane is the image. So where did our x dimension go? Well, suppose we take some vector, random vector blue. Oh, I have to explain what black is. Black here in the domain is the vector -2, -1, 1. So that's my null space. It's over here. So this black vector is the basis for the null space. So the null space is the line that runs through this black vector. And I'm not going to draw it in because it'll make everything a little bit complicated. It'll make the picture messy. There's enough stuff there as it is. So take some random vector v, and that's my blue vector here. And I can break that up into something times I, the red vector, plus something times j, which is the blue vector, the green vector, plus something times the null space vector, right? So I and j and the null space vector, those are all linearly independent. So they span the entire space. And so every vector v can be written as a combination of ai, of a linear combination of I hat, j hat, and the null space. And this part is the orange vector here. So what's m times v? So that's m times the blue vector. Well, that equals m times the orange vector, plus m times the black vector. But the black vector is the null space. So m times that equals 0. So the blue vector and the orange vector differ only by a vector that's in the null space. And so they go to the same place, right? Orange plus blue is orange plus black, but black goes to 0. So the blue vector and the orange vector both get mapped onto, so m times blue equals m times orange. And that's this vector down here. So this was what, 4 times red plus 2 times green. And if you go 4 times red plus 2 times green, you'll end up on that vector. So if we think about the null space, right, that goes through the tip of the orange vector, there's a whole bunch of vectors that are the orange vector plus something in the null space. And all of that, this entire line just gets mapped down to 0. So everything on this entire line gets mapped to the same vector that the orange vector does. So that's where our extra dimension is, right? This entire line gets squished down to the orange vector, and then that whole set gets mapped onto this orange vector down there. And that's where our missing dimension went. So finally, determinants for square matrix. Every square matrix is a determinant, and that, but coupling that gets more involved the bigger the matrix is. If this was, I think it's 312 is the linear algebra class, we would go into this in detail, but I'll at least show you how to find the determinants of these things. So this was the first vector, the first matrix. These turned out to all be linearly independent, right? This is the matrix from the first example. So how do we find the determinant? The first thing we do is we set up what's called the checkerboard pattern. Like that. So it's plus, minus, plus. You start with a plus in the upper left, and then minus, plus, minus, plus, minus, plus, minus, plus. Okay, so the determinant of a 3 by 3 matrix You calculate it as a sequence of determinants of 2x2 matrices. Generally, when we want to do this, you want to pick a column or a row that's got a lot of zeros on it. So I'll pick the first column, and I take this number with this sign, so +1, times the determinant you get when you look at the matrix that when you've deleted this column and this row. So 1 is in the first column in the first row, so we look at the matrix that has not that you get when you delete the first column, the first row, and so that's the matrix 1, 4, 6, 0. And then we take minus times 0, so this sign times this number times the determinant of the matrix you get when you delete. Now 0 is in the here, so I want to delete the first column and the second row, so that'd be 2, 3, 6, 0. And then we take plus times 5, determinant of what you get when if you take 5, we want to delete the third row and the first column, so we get 2, 3, 1, 4. And these are all 2x2 matrix, so the determinant of this 3x3 matrix is 1 times 0 minus 4 times 6. Right? The determinant is 1 times 0 minus 4 times 6, minus 0 times this. This is just 0, so because 0 times anything is 0, plus 5 times 2 times 4, which is 8. 2 times 4, right? This times this, minus 3 times 1. So the determinant of M is minus 24 plus 5 times, now this is 8 minus 3, which is 5, which is minus 24 plus 25, which is 1. Right? These columns of M are linearly independent. Determinant of M does not equal 0. That's the same thing that we had at the end of the last lecture. Here, the determinant, these columns were linearly dependent. This was the columns in the second example. We should find that the determinant is 0 here, but we can calculate that. Set up your checkerboard. No zeros in this matrix, so we'll just take the first row because it's got a bunch of 1s. So what's the determinant of M? We take this 1 with the plus sign, so +1 times the determinant of the matrix when you delete the column in the row that this 1 is in. So 1, 3, 2 minus 4. And then you take minus, that's this sign, times this number, times the determinant you get when you delete the column in the row that the -1 is in. So that's 1 minus 3, 3 minus 4. And then plus the 1 here, the third column, times the determinant of 1 minus 3, 1, 2. So the determinant of M is, well, 1 times something is just 1. And the determinant of this matrix is 1 times -4, minus 3 times 2, which is -6. Plus, right, minus is a plus, the determinant of this matrix, which is 1 times -4, which is -4, minus 3 times -3, which is -9. Plus, this is +1, 1 times 2, which is 2, minus 1 times -3, which is -3. So the determinant of M is -10 plus 4 minus -9 is 5, plus 2 minus -3 is 5 equals 0. Determinant equals 0, columns are linearly dependent. And so that means you're going to have a null space, because if the columns are linearly dependent, then the basis is going to of the image is going to be less than 3, and you'll have a parameter. So how do you find the determinant of the matrix below? Well, it's the same procedure, right? You'd set up your checkerboard, plus, minus, plus, minus, plus, minus, plus. Nope. Sorry about that. You set up your Checkerboard carefully. This one would have to be a minus, right? Because it's a plus, plus, minus, plus, plus, minus, plus, minus, minus, plus, minus, plus. So a checkerboard where everything's alternating like that. Take a row or a column that's got a pair of as many zeros as you can. So we'll look at this one because it's got 2 zeros. So the determinant of this matrix, if we call this M, be 2 with its sign. So minus 2 times the determinant of the matrix you get when you delete the row in the column that 2 is in. So that's 0, 1, 3, minus 3, 2, 1, 1, 4, 1. So this matrix is what you get when you delete the row and the column that your 2 is in. And then we'll take plus 3 times the determinant of the matrix you get when you delete the row and the column that 3 is in. So that would be 1, 0, 1, minus 3, 2, 1, 1, 4, 1. And then you get minus 0 times something plus 0 times something. And I don't really care what they are because 0 times anything is 0. And then you calculate this out because now this is a 3 by 3 matrix and you can figure out how to find the determinant of that. And then it gets really tedious. We're not going to actually try and find determinants of matrices bigger than 2, I don't think, because it's just numerical grind. Anyway, importance of determinants. Determinant of M equals 0 means the column is linearly dependent. Determinant of M does not equal 0 means the columns are linearly independent. And that is that.